11:15. Is that right?
It is a second talk, sir.
No, the session ends at 11:15. Is that correct?
Yes.
Yes.
I see. Okay. All right. Okay. So I'll try to stop a few minutes earlier. So maybe if there are any questions, we can take it towards the end. But if any of you want to ask questions in between, please do feel free to unmute and speak and ask a question. So just to quickly introduce the research that we do in our group here at IIT Hyderabad. So we broadly work in the areas of deep learning, machine learning, computer vision. So within these areas, we look at understanding why deep learning works. That's the theory of deep learning. Explain machine learning methods and deep learning models, as well as learning with limited supervision. All of these three are foundational directions in which we do efforts. And on the theory of deep learning side, we have done some work on understanding the layer-wise Hessian of deep neural network models, some modular batch selection for training deep neural networks, connecting noise and optimality in neural networks, so on and so forth. And in the explainability aspect, we've been looking at use of causality for neural network explanations. We have a method for visual explanations of convolutional neural networks. And more recently, we've also been looking at the connection between adversarial robustness and explanations. And all of these works have been published at premier venues, including Europe's ICML, ECCV, CVPR, so on and so forth. And on the learning with limited supervision side, which is perhaps the focus of this talk, we've been looking at continual learning, open world object detection, few shot learning, zero shot learning, so on and so forth. On the application perspective, a lot of our applications are derived from the project funding that we receive. But we've been looking at security and surveillance, agriculture, autonomous navigation, aerospace, so on and so forth. And we're grateful to all our funding source bodies, both from the industry, government, and defense labs, who have very kindly sponsored our research efforts. Okay, so with that very quick introduction to what we do here at IIT Hyderabad. So what I'll do for the rest of the session today is talk about why learning with limited label data or limited supervision is important. What does it mean? I mean, what does it entail in terms of developing machine learning models? Then I'll try to go one level deeper into some of our recent efforts broadly in the space of continual learning, so that there is some continuity in the talk. And if time permits, towards the end, I'll try to take a quick walkthrough to several other efforts of ours, but maybe depending on time. And I'll then conclude with some open questions and challenges that may be of interest to any of you who actively work in this field. Okay, I think it's common knowledge. I'm quite sure all of you know that very broadly speaking, machine learning has a few common paradigms. You have supervised learning on one side, where you're provided with data and labels, and the model has to predict a label, be it a discrete label or a continuous value for a given input. Then in unsupervised learning, you can talk about tasks like clustering or grouping, or also you can talk about more recent developments such as self-supervised learning, where you try to predict a part of the data itself for a given data point. So there are no labels to predict. You just have to work with the data by itself. And of course, reinforcement learning has this paradigm of a delayed reward, where you learn an optimal policy that achieves a certain reward after a certain point in time. I'm quite sure all of you are comfortable with this basic paradigm, right? And all of us also know that the success of machine learning, deep learning today all around us is in the supervised learning regime, right? So if you provide enough amount of labeled, curated data, we all know it's possible to make machine learning models and deep learning models work in practice. With a certain amount of hyperparameter tuning and engineering, you can probably make these things work in practice, be it computer vision, be it speech, be it natural language processing. We know that there has been immense success in these domains over the last few years. I'm not sure how many of you know this, but there was an interesting analogy that was given by Yanle Kun. Yanle Kun was one of the Turing awardees for his contributions to deep learning about 2-3 years ago. So he looked at these paradigms of deep learning, machine learning, and compared it to a piece of cake. And his analogy is that supervised learning is like developing the frosting for the cake. Reinforcement learning is like the cherry on the cake. And unsupervised learning is actually the cake itself. Right? For many years now, We have developed the frosting. We probably worked to some extent on the cherries. The question now is to how do you learn when there is almost no labels itself, which is the actual cake that we want to bake. Just to add some detail to this analogy, it's not just one monolithic entity that goes from supervised to unsupervised learning. The cake has several layers. You just cannot talk about unsupervised learning where you have only data and no labels. There could be different kinds of scenarios depending on what kind of label information you have, what class has what labels, what class doesn't have as many labels, what kind of additional information you have. All of those things leads to a very layered approach of this cake. It's not just a monolithic cake, but several layers depending on what kind of supervision you may have to solve these problems. So if one had to compare supervised learning versus say how we as humans learn, right? So we all know supervised learning, the way we understand machine learning, the way deep learning is used, deployed, is that you have a fixed data set with a fixed set of labels, and then you train a model and then use that model in practice. There are so many aspects and so many algorithms for doing this, but this is the standard paradigm of supervised learning, where the data set is fixed and there is a fixed set of classes, and then you try to learn a model that works for that data set given those class labels. Right? So that seems like such a constrained setting. Now let's try to see how humans learn. Firstly, humans learn from available data with or without labels. Right? So it's not like if somebody tells you to learn a tiger, you will say, go label 1,000 tiger images for me. Right? If some images are labeled, some images are not labeled, it's okay. We learn from whatever is available. Right? So we're very good at something like this. We can refine what we have learned using newer data without forgetting the past significantly. Right? So you may have learned something in the past, and now you get some newer information. Then we refine our understanding without forgetting the past significantly. Right? We're reasonably good at doing something like this. Sometimes we may not even need data to learn. You may not need images or text or speech. You may just need some descriptions. Right? So I can just tell you a zebra is like a horse with stripes. Right? You may never even see a zebra. Right? But just with those descriptions, you probably have a mental model of how a zebra looks. We can learn just from descriptions itself. We can learn interactively by asking questions. In this session, if you have a question, you'll probably ask me and I'll respond. Right? And you know when to ask a question, when a doubt is going unanswered and you have to step in and ask a question. And that interactive process of learning helps you build better knowledge. And finally, you also have the ability, as humans, we all have the ability of saying, I don't know. It's not like if you have a fixed set of classes, you only have to predict one of those n classes. You have the ability to say, I don't know, and perhaps ask for more information to learn a new concept, and many, many more such situations. The entire human learning process is far richer than just have one set of data and one set of labels. Right? But strangely, that's the paradigm of machine learning that we've been working with for decades together now, which has been successful around us. And it's time for us to move forward beyond this traditional supervised paradigm. So if you look at some of these human learning paradigms on the right side, they're all keywords that become different settings while you talk about learning with limited supervision. Continual learning is about refining your model using newer data without forgetting the past significantly. Zero-shot learning is where you learn only from the descriptions of data without access to the data itself. Active learning is where you try to learn interactively by asking for labels only when you need. Open set or open world learning is about the ability to say, I don't know, and ask for more information to learn a new concept. All of these are different settings when you talk about deep learning with limited supervision. Okay, so let's look at some of these settings in more detail. So as I said, standard supervised learning is where you have X and Y data and your labels coming from some distribution D1. You train a model or a learner, you get a model, and then you use that model on a test set, which also comes from the same distribution. That's the assumption when you talk about standard supervised learning setting. Now, there are many variants now depending on what information you have. If while training, you have XY, XY, XY coming from different distributions, each of which corresponds to different tasks. Right? For example, you could have a face image, but then you may want to recognize the person's identity. You may want to recognize the person's age. You may want to recognize the person's pose. You may want to recognize the person's expression. So many things given a single X. So this is what leads to multiple tasks. Then you train a single model, which can now infer based on, now if you pull X1 from D1, X2 from D2, and Xn from Dn, it can now predict what we typically refer to multitask learning. Transfer learning is where you have a source task and a target task. The source task, the data comes from a distribution DS, and in the target task, the data and the labels come from a distribution DT. Then you've trained a model on your source task. Now you want to see, how do I transfer the knowledge learned from the source task in the form of this model into a target task? Right? And that's what you want to improve performance on. Your final goal is to improve your performance on the target task. Domain adaptation, which is very similar to transfer learning, very subtle differences between transfer learning and domain adaptation. In domain adaptation, you need not necessarily have a model from your source task. You may directly use the data points from your source domain and use that for improving the performance on your target domain. Right? All of these are different paradigms of learning with limited label data. Right? When would you do domain adaptation or transfer learning? When you think you may not have enough data in your target domain, and you may need to borrow data from other domains so that you can improve your performance on the target domain. Then you have K-short learning. K can be 0, 1, few, so on and so forth. So this could be 0-shot learning, 1-shot learning, few-shot learning. All of them have a similar paradigm. So you have a total of n classes given in your setup, of which m are observed during your training time, and the remaining m plus 1 to n, you only have K samples given to you. K could be even 0, K could be 1, K could be a few samples. Right? This is very common, right? If you're recognizing animals, you're probably going to have lots and lots of images of dogs and cats, but you probably won't have enough images of, say, a yak or a llama or something like that. You may just have 1 or 2 images here and there for these kinds of rare classes. So now you want to train a model which performs well on all of these classes, even if you don't see any examples from these m plus 1 to nth class. In continual learning, you initially have data coming from a distribution task T1 and distribution D1, and you train a model which works only on data from that distribution. Then over time, you have a new task where the data now comes from a distribution D2, and you now have to train a model that works both on data that come from D1 and D2. And as you go through in time, you finally may come to a task Tn where the data and labels come from a distribution Dn, and you now have to make your model work on all the data so far. And at this point in time, you may not have access to the data from previous time steps. This is how humans learn, right? So you probably have learned something when you were 5 years old, 6 years old. Right? You cannot store all your images in your brain, right? It's not like you're storing every image that you've seen in your brain. But I mean, if it's an important thing that you're using on a daily basis, you don't forget that, right? If somebody taught you a dog is a dog at the age of 5, right? You can still recognize a dog, even though you may not see an image of a dog right now. Right? So that's continual learning. And finally, more recently, there have also been paradigms of domain generalization, where you have a source domain, 2 domains rather, TS and TT, where you have data distribution from TS and TT. You train a model, and now you test on a different distribution, DT plus 1. Okay, so that's a completely different domain altogether in this particular context. So you want to learn on a couple of domains, but now you want to test on a completely different domain which you've not seen so far. It's like if you had autonomous navigation, you have learned to classify objects using data from the daytime. Now you have to make this model work on nighttime without having any images of nighttime, right? So that's domain generalization for you. So in our group here at IIT Hyderabad, we've been looking at all of these aspects of learning with limited label data. We've been looking at 0-shot and few-shot learning, where we have papers in CVPR, WCV, multiple places over the last few years. We've been looking at active learning, continual learning, domain adaptation, domain generalization, just generating data for domains where you may have very sparse data. And all of these together become important approaches. I don't think there is a single answer to solving a problem of learning with limited supervision. It depends on what kind of supervision and what kind of data you may have available for a given application. Okay, so what I'll try to do over the rest of this talk now, so I think maybe I have about 35 minutes or so, is I'll try to talk about a few of our recent efforts in this direction, most of which are in the continual learning space, and go into details of our methods in this space, and time permitting, I'll try to walk through some of our other efforts towards the end. So the first work that I'll talk about is meta consolidation for continual learning. This work was presented at NeurIPS of 2020, joint work with Joseph, who's a PhD student of ours at IIT Hyderabad. So as I mentioned, continual learning is a setting where you have data and tasks coming continuously over time, and you have to keep updating your model without forgetting how you performed in the past or on your tasks or classes in the past. This phenomenon for neural networks was actually discovered in 1989. Okay, this is not something really new. Neural networks have been there for a long time. So a couple of people, McCloskey and Cohen in 1989, so they had a paper called Catastrophic Forgetting in Connectionless Networks. So they conducted a bunch of experiments, and one set of experiments was they taught a neural network model an equivalence between objects. They taught it that whenever a locomotive is shown, the neural network model should predict dish towel. Whenever a window is shown, the neural network model should predict reason. Whenever a bicycle is shown, the neural network model should predict tree. Okay, remember, at that time, there was not too many data sets. It was just a simple experiment that they conducted. And once they trained the neural network model, they later changed these associations. They said now that A, which is locomotive, window, and bicycle, has a different mapping to cloud, book, and couch after some time. Okay. So when they did this, they found that now the model cannot go back and retain the previous associations in any way. Okay. Interestingly, they found that when humans are given a similar context, humans also forget, but the forgetting is gradual over time. Right? If you can see this red curve here on the right-hand side, right? This forgetting is gradual over time, but when a neural network learns this, the forgetting is catastrophic. Right? So it starts with something really, really strong and immediately starts forgetting the past, which is very, very different from how humans learn continually. This loss of old knowledge is far too sudden than gradual in neural network models. This is what they observed at that point in time. And this is one of the primary challenges of continual learning, that when you train a neural network model on a set of classes now, and newer classes come tomorrow, you may not have access to data from previous classes. Now, when you train a neural network model on the new classes, it happens that the neural network model forgets how to classify the previously seen classes. To address these, there have been several methods that people have proposed, but there are two fundamental ideas here, which almost induce a trade-off. One is, when you update your neural network model for newer and newer classes, it's important to have stability. You shouldn't change weights too much, because if you change, you won't be able to recollect your old classes. Remember, at the end of the day, what you predict is a function of the weights of a neural network. Right? So that's the stability concept there. The other thing is, you also want some plasticity. You also want to allow the weights to change. Otherwise, you cannot learn the new concept. Right? So you have stability on one side, where you don't want things to change too much. Then you have the plasticity on the other side, where you do want the weights to change so that it can learn newer and newer concepts over time. We found that this results in a trade-off between stability and plasticity, because they are in some sense conflicting objectives. How do you achieve stability without rigidity, and plasticity without chaos becomes a question. How can a neural network remain plastic in response to significant input, which means it allows itself to adapt to newer input, yet stable in response to irrelevant information? So it should be stable if there was irrelevant information, so that the stability can help it perform well on previously seen tasks. But it should be enough plastic to change for significant input that comes in at this point in time. And how does the system learn to switch between a plastic mode and a stable mode when newer data comes in? Right? All of these become important questions to answer. A lot of the existing methods try to focus on these kinds of things to come up with different ideas. So very broadly speaking, one could categorize existing continual learning methods in a few different kinds. One kind of a method, one kind of an approach is called model growing, where given an architecture, whenever a new set of tasks come or new set of classes come, you increase the model capacity, introduce a new layer, or in a given layer, introduce a new set of neurons to learn the new class, right? So this is one way of doing it. But the problem with this kind of an approach is you cannot keep growing a model eternally. It's going to become too big for using such a model. So approaches have that limit. They are popular to some extent, but have their own limitations in practice. Parameter isolation methods explicitly identify important parameters or weights for each task and then try to adjust only them for a given task and leave the other parameters aside so that they can be used for the previous tasks. Regularization methods penalize parameter variations. So when they are updating your weights, these regularization methods say that you should not go too far away from the previous weights using some kind of an L2 weight penalty between the previous weights and the current weights, or so on and so forth. Knowledge distillation methods do something very similar to regularization, where they try to ensure that the current model that we have that is being updated based on current data is similar to the previous model that was learned in a previous training state. So the previous model is looked at like a teacher and the current model is looked at like a student. And you don't want the student model to go too far away from the teacher model from the past. Okay, these are knowledge distillation methods. And finally, you have rehearsal methods, where while you cannot store all the data from the past, can we store a few samples from the past so that once in a while we can replay them and see whether we are doing well on them. Okay, so this is a common approach. It's called memory replay or rehearsal methods. And often in practice, people even these days, especially with newer methods, people combine several of these methods to actually make them work for continual learning settings. So I'll go on to this particular work that we had called meta consolidation for continual learning. It was called Merlin, as I said, presented at NeurIPS of 2020. So this work of ours came from the hypothesis that the human brain does not store all your images, right? So it's not like if you've learned something in the past, you have all that information stored with you. Right? We perhaps store all of this knowledge in some kind of a compressed form. And whenever we need to recall, remember, we think, right? Sometimes when you've seen something very far back, you spend a few moments thinking and recollecting. And then you probably, if something was in compressed form in your brain, you perhaps decompress it and then use it in practice, right? So this is, in a sense, how human learning works. So this inspired by that. I wouldn't say this is exactly how the human brain works, but our method is inspired by this kind of a cognitive understanding of cognitive processes. So what we propose is that we try to use a meta learning kind of an approach, where we learn models that can predict for a given task, and then try to store, try to learn a variational autoencoder, which can store a compressed form of the model and then generate a model whenever it's required for a new task. Okay, that's the overall idea. I'll hopefully make it clear over the next few slides. So as you can see, we assume now that the weights of a neural network psi for solving a given task, and by the way, I should probably clarify when I say task, task means different things in continual learning. It could mean a new set of classes. It could mean a new set of domains. It could mean a totally different task altogether. But the most general setting is called class incremental learning or class continual learning, where we assume that every new task comes with new classes. So for example, task 1 could be learning dogs, cats, and lions. Task 2 could be about learning tigers, elephants, and crocodiles. Task 3 could be about learning yak, zebras, and horses, so on and so forth, right? So each task, you're getting newer and newer classes, and you have to keep updating your model without forgetting how previously seen animals looked. So the weights of a neural network for solving task T, we assume, come from some meta distribution P of psi given T. So we assume that the model itself can be generated. I'm not talking about the images, I'm not talking about the data. We are saying that the model, which means the weights of a neural network itself, can be generated by another neural network, which we call as a meta distribution. And then we continually learn in this parameter meta space on this meta model with some consolidation. Okay, that's what we try to do. So this particular work operates in what is known as the online continual learning setting. The online continual learning setting is where when new data comes in, you're allowed to make only one pass through the new data. because it's a streaming kind of a setting, right? So that's the assumption we assume, which is actually natural and more challenging. You're not allowed multiple passes over the new data. So our method works in task aware and task agnostic settings. I think I'll skip that perhaps in the interest of time, but we also show that this can work when your task is new classes or new domains. And we also show that using this kind of an approach, you can automatically do ensembling of models, right? I'll probably describe each of these over the next few slides. So here is our overall approach. It's quite, there are quite a few symbols here, but the idea is fairly intuitive. So what we try to do here first is assuming that in the beginning, you have data from a certain task, right? XT, YT, you have a data from a certain task. Now, what you do is you sample multiple training data subsets from this data and train different models. So you train B different models by randomly subsampling training data from your given training data. So if you have, say, 10,000 training data points, you randomly sample 1,000 training data points and train a model. Then again, randomly sample 1,000 data points, train another model. Then again, randomly train 1,000 data points, train another model. We train B such models. Now, once you have trained B such models, this becomes our training data to actually learn our meta model, right? So we learn the parameter distribution using a variational autoencoder kind of an approach, where each of these model weights that we had learned come into our variational autoencoder. So the weights of the neural network become using a variational autoencoder loss strategy, and you now learn these latent variables Z using this kind of a variational autoencoder. Once we do this, we consolidate the meta distribution. I'll talk about what we mean by consolidation on the next slide. But once we have done all this, finally, you've trained the model. What you do at inference when a new test data point comes is you just remember this is a variational autoencoder, which means it's a generative model. So now if you randomly initialize Z with some vector, you provide this to this decoder, it's going to generate your model weights for the given task that at hand. Now you use those model weights to make a prediction on a newer data point. Now the interesting part of this kind of an approach is at test time, you can give multiple Z values because it's randomly sampled from a distribution, generate multiple models and use all of those multiple models to make a prediction and average your output and get robustness in your output by ensembling. Right? So it automatically, this kind of a generative approach of using a VAE to capture the meta model allows us to automatically ensemble at inference. Now coming back to this consolidation. So the way we do the consolidation is quite simple. Let me perhaps not necessarily go through the math. I'll go back here and tell you. So once you've learned this variational autoencoder, to consolidate this meta distribution, what we do is we have a few samples from previous tasks that we store, as I mentioned, or rehearsal kinds of methods allow us to store a few samples in a buffer. So we have those samples. We generate a model using this trained VAE, use that model to make a prediction on those stored samples and see how well we do. Based on the loss on that particular task, we backpropagate and refine this VAE, and that's what we mean by consolidation of the variational autoencoder periodically to ensure that it works well on previously seen examples. Okay, this is what we call as meta consolidation. As you can see, you could now imagine that the Z here is like some compressed form of knowledge that we're storing. As and when we need, we decompress it, generate a model, and apply that model at inference when a new test data comes. Okay, that's why I said this is inspired from a cognitive kind of a thinking. And using this kind of an approach, we show that we can get very strong performance on classification on multiple data sets, MNIST, permuted MNIST, CIFAR 10, CIFAR 100, mini ImageNet, so on and so forth. We significantly outperform most other state-of-the-art methods on both accuracy and forgetting measure across multiple data sets. We also show that using TSNE visualizations, that the model weights that are generated by the model are fairly consistent in terms of tasks. So if you look at the right image, each color refers to the model weights that we generated for different tasks. So you can see that all colors are clustered together to say that the model weights generated for a particular task are similar to each other and are fairly distinct from the model weights generated for other tasks using our method. Okay, so if you're interested more in this kind of an approach, you can look at our website for more details, and code is also available if you would like to take this forward or try it on your own. Okay. A follow-up work, which was also done in collaboration with MBZ, University of AI in Abu Dhabi, was published at TPAMI a few months ago. And this work is called incremental object detection via meta learning. Okay, so once again, we are talking about a continual learning setting where newer and newer classes can come over time. Okay, so this is the problem setting that we are looking at, which is incremental object detection. So in incremental object detection, you've initially learned to detect a few classes, like bird is a first class that you learn to detect. After some time, you find a new class called person that comes into the picture. Until then, you did not have the data or the labels for that particular class. Now you want to incrementally learn person without forgetting how to detect a bird. Okay, that's the idea. And remember, when you do this incremental learning, you may not have access to the annotated data for birds. Okay, that's what makes this challenging. If you had the data from the past, it's quite straightforward, but you cannot always do that in a continual learning setting. So the simple idea of our approach is to do what is called gradient preconditioning. We assume now, if you look at this particular, this is just an intuitive illustration of our approach. If you consider that the task-wise gradients that we get in our model is built on top of the faster RCNN object detector. So you could assume that that's the baseline, although the method can be used for other kinds of detectors also. We show it with faster RCNN, however. So you can see here there are two blue arrows, which are the task-wise gradients. So the task-wise gradients are, for each task, you get a different kind of a gradient. Right? So for the previous objects, you get a gradient in a certain direction. For the current objects, you get a gradient in a certain direction. Now the problem is if those tasks are in different directions, you find it hard to find a model that works for both of these tasks, which is the problem in continual learning itself. So what we do here is to precondition the gradients using a technique called warping, which I'll talk about in the next few layers. And then we use the average of the preconditioned gradients to update our model, thus ensuring that we can learn continually without forgetting. So the overall idea is to do meta learning to reshape the gradients so that the information across tasks are optimally shared and you don't forget the past. Okay? We'll step into one more level of detail now. So if you now assume that whatever object detector model you have, let's say faster RCNN, whatever model you have, let's say it's parameterized by some parameters theta. We know that the standard gradient descent update is given by theta prime is given by theta minus alpha times gradient of L with respect to theta, where alpha is your step length or learning rate. So in the warped update, what we do is we multiply this Jacobian matrix, this gradient, with a preconditioning matrix, which we define as P. Okay? And the way we do this preconditioning matrix is by dividing our architecture into two kinds of layers. I will show the architecture diagram in the next slide. It should be clearer then. Into a task layer and a warp layer. Okay, so and we use the warp layer to condition the gradients that go back to the task layers. Okay, let me show you this. So assume now that, look at this this part what I'm pointing out. Assume now that there was a previous model which had a certain backbone for the faster RCNN, and then had the ROI head, the region of interest head in the previous RCNN. Now in the current task, which is what you see as the yellow box here, given a new image with some newer classes, you give this as an input to the same backbone network, okay, whatever that be, ResNet 18 or whatever that network be. Okay, that goes into a feature detector, okay, which is again the same. That goes into a RPN or a region proposal network that's used in a faster RCNN, okay, which then goes into a fast ROI head, where you take all these region proposals which are given into a separate convolutional network which classifies. This is the standard faster RCNN pipeline, right? So now inside the ROI head that's done after the region proposal network, what we do is, given a network there, we introduce these green layers called the warp layers. The blue layers here are the task layers. That's the layers that stay as they are. The green layers are what we introduce as warp layers. What do you do with warp layers? I'll talk about it in the next slide. Firstly, the task layers, which are these blue layers here inside the ROI head. Okay. We train using a standard loss, right? You train using your classification loss plus region proposal loss, plus we introduce a distillation loss to ensure that those layers maintain the weights with respect to the previous task. As I said, knowledge distillation is one of the approaches to do continual learning. Now for the warp layer, we also use the features stored from the past. Okay, so we try to ensure that if you had those replay kind of examples that you stored in a buffer from past tasks, now you try to propagate them through the warp layer and see how the prediction of the model changes for those previously stored examples, and now warp the weights or use this kind of a loss called the warp loss. Warp loss is actually, the terms here are exactly the same as a faster RCN and loss. The only difference is that we do it with respect to the previously stored examples and not necessarily just the current examples alone. Okay, that's the main difference. So we allow the warp layer to now tell the network that this is how the model performed on previously seen examples. Now use this as a preconditioning to accordingly adjust the gradients and ensure that the gradients don't change too much from how we performed in the past. Okay, that's the main idea of this warp layer. So this is just the algorithm put together with all of these things. So you periodically use the warp layer. You don't use the warp layer always. So you all of these are standard continual learning paradigms. So you update your parameters for the task layer for a given task using standard gradient descent. And periodically, this condition I mod gamma equal to 0 tells us that you do it once in a while. Okay. Once in a while, you update the warp layer to ensure that that conditions your gradients to not go too far away from the weights that worked on the previous task. Okay, that's what we try to do in this particular scenario. So we test this approach on multiple object detection datasets like Pascal VOC and MS COCO. Pascal VOC has 20 object categories. So we tested on multiple variants of these settings, where initially we learn 10 classes, then we keep adding one class in each task then on. Then we initially learn 15 classes, try adding one class then on. Then we also try learning 19 classes and then add one class and see how the model performs. Then we also tested on MS COCO, which has 80 categories, where we initially learn with 40 classes and then learn one class at a time as we go forward. Okay, so and for all of these, we measure the mean average precision or the MAP of the detector to judge the performance. And we show that with this kind of an approach, we significantly outperform an earlier method, which was published in ICCV 2017 for incremental learning of object detectors. That was the only known work before we did our work, and we outperformed that on multiple of these settings, as you can see here. I'm not going to go over the tables here, but we outperform the previous method on all of these. If you're further interested, this paper is also publicly available, and the code as well as the entire paper is also available on arXiv and GitHub if you're interested further. Okay, for the last piece of work that I'm going to describe today, it's a more recent work called Open World Object Detection, which was presented at CVPR 2021 as an oral, once again joint work with MBZ, University of AI at Abu Dhabi. So Open World is an extension of continual learning with a twist, with some constraints which make it harder to solve the problem. Okay, so let's see what that means. So now let's assume that you have this x-axis here, which is the axis of time, which means over time you get some newer and newer data. Okay, that's the setting here. Now at a certain time t, you have some known objects, which are new objects which come into the system, and then you update your model based on those new objects. That's your standard continual learning setting. But now what we assume here is that it's possible that among these new objects that come, there are also some unknown objects. Right? We don't know what they are. Nobody has told us what they are. These blue circles represent newer objects which somebody has labeled for you. But the data also contains other kinds of objects which the person has not labeled for you. Right? Very realistic, right? So it's possible that in the real world, when you get data, some of the objects may be labeled, some of the objects may be new, nobody knows how to label, or nobody has labeled them for you. Right? So now the model has to first of all detect that these are unknown objects. Okay, that's not trivial for a machine learning model to say when it doesn't know something. But we don't stop there. This is typically called as open set learning. To be able to detect an unknown is called an open set learning. But we don't stop there. We do open world, where among those unknowns, if we can get labels for some of those, we'd like to get those labels and update the model for some of those unknowns for which labels can be made available. So open set is about detecting unknowns. And if for some of them we can get labels, we'd like to now update them and then learn a new model without forgetting the past again, right? So that aspect of continual learning remains here. Okay, you may not have access to data from the past, So you may forget from the past and you don't want to do that. Okay, but this is the overall setting that we talk about. Okay, one question you could have is this too manufactured? Do people really need such models in practice? In fact, after we published this work, we've had interest from several organizations around the world who have wanted this kind of a setting. I'll give you one specific example from an organization that contacted us after we published this work. This was an organization that does deep sea exploration, right? So it's an organization based out of California in the US. And they, similar to the Mars rover, they also have a rover that goes on the seabed, on the ocean floor, right? And they just keep recording video all the time, right? So that's all they keep doing, right? And often what happens in such kind of environments is that they see newer and newer organisms each day, right? So they know to detect a few things, but then each day there is something new that comes, and it becomes important for them to say that something is unknown, and if required, probably send those images to an expert on the ground and ask them to label it and update the model so that it can detect better under the sea, right? So you could now imagine this to be for any autonomous vehicle that's going through an unknown environment, right? So you can probably detect a few objects, but a few other objects you may not be able to detect. So how do you say that I don't know what this object is? How do you get the label for it and update the model without forgetting? Okay, that's what we refer to as open world object detection. So this particular problem can be looked at from multiple perspectives. You can call it as related to continual learning or incremental learning. Continual and incremental learning are largely considered synonymous. Okay, so then you have open set learning on the other side, where in open set learning, you only try to detect an unknown. That's all. You don't try to learn further. You just try to say, I don't know. That's all you try to do. So what we are operating with here is a common open world object detection, of which there was no work to the best of our knowledge when we first did this. So we operate with a faster RCNN architecture, which looks somewhat like this. So you have an image, you have a backbone network, you get a feature, you provide it to a region proposal network, then you take those features and give it to an ROI head, the region of interest head, to which you give each region proposal. And then since we're talking about object detection, you have a classification head and a regression head, which classifies and also localizes the object in an image. Okay, this is your standard faster RCNN pipeline for doing object detection. So we primarily make three changes in this architecture to achieve our goal. We change this RPN network here into an unknown aware RPN. Then we change this particular last layer of this ROI head to do something called contrastive clustering. And we finally change this classification head into what we called an energy-based classification head to achieve our purpose. So I'll talk about each of these briefly before I show you some results. So in this context, this particular layer within the ROI head, where we do contrastive clustering, what we try to see is if we can cluster data in such a way that the unknowns automatically go to one corner of your feature space. So you have some known classes. If you push them all close to each other, hopefully the unknowns, sorry, I think my battery is low. Please just give me one moment. Let me just plug my laptop to the charger. Please give me one moment. Okay, sorry about that. Okay, so in this particular layer, so we do contrastive clustering to push the unknowns away from the known classes. That's one of the things that we do. And the way we do that is by introducing something called contrastive clustering. And the loss is very simple. We use a margin kind of a loss where we say that if a given product, if a given feature, if a particular class is close to a prototype, then you have a certain distance. And if something is far from all the known class prototypes, then you ensure that it's at least a certain margin away from all of these classes. Can we use a simple margin kind of a loss to implement this contrastive clustering? Okay, I won't go into the details of the algorithm, but that's the core idea. The second thing, as I mentioned, I said, is that in the RPN network, we also introduce something called an unknown aware region proposal network. And the way we do that unknown aware region proposal network is we now, given the region proposal network, typically the region proposal network outputs a bunch of region proposals. For region proposals, which are some bounding boxes in your given image, which do not have an overlap with any known ground truth object, we call them as an unknown object. So the model thinks that there is an object there, but it does not have an overlap with any of the ground truth objects that we know. Then we assume that it must be an unknown object. Okay, fair assumption to make. That's what we try to do here. And to implement this, we use an energy-based approach. This is what is the typical equation of the Helmholtz free energy. And you could connect this to the logits or the final outputs of a neural network using this kind of a formula. This is exactly the same as the Helmholtz free energy equation. Only thing is the integral is replaced by the summation. And this energy is replaced by GI, which are the logits of your neural network. Logits are the outputs of the neural network before you apply softmax, before you make it a probability. That's the final outputs that you get. So we refer to this as the energy function in our particular setting. Then the probability that's associated with this energy function could be simply given by a temperatured version of your typical softmax activation function, where you do an exponent of the logit with respect to some temperature T divided by the summation of all of these logits. And that's your probability. So now using this kind of an approach, we show that if you learn this kind of an approach, we see that all the unknowns automatically have a probability distribution that's different from the probability distribution of the known classes. This automatically helps us separate the unknown classes from the known classes. So this is what we introduce in the energy-based classification head here, where we first use this energy-based distributions to decide whether a class is unknown or known. And once we know a class is known, we then use the standard classification head to decide which class label it is. Okay, so it's a bit of pre-processing there using this kind of an Helmholtz free energy. So it's a standard way to do some kind of an out of distribution detection. And that's what we use here to find out what could be an unknown class in this kind of an architecture. So we test this approach on the MS-COCO dataset, where we assume that our task 1 contains all the 20 classes from Pascal VOC. And then task 2 contains other kinds of classes. In task 2, we have outdoor accessories, appliances, and trucks. In task 3, we have sports and food. In task 4, we have electronic, indoor, kitchen, furniture. Right? So over time, you're probably exposed to newer and newer environments, and each of them brings newer and newer classes which you have to learn continually. Okay, that's the setting that we operate in. We measure performance for this using a metric called wilderness impact. I'll look at the paper for that, but both of these metrics that we use are based on previous work on open set recognition. And we also use something called an absolute open set error, which counts the number of unknown objects that get wrongly classified as a known class. And we also measure the goodness of detection using mean average precision. Okay, just to give you a qualitative example of how this works. So initially, we assume that after a certain task, we have not learned any fruits at all so far. Right? Our model was never exposed to fruits. It was only exposed to people. And we know how to detect a person, but we don't know how to detect fruits. Then we get such an image. Then the model detects the person, draws a bounding box around the person, but now it also detects that there are other objects which, because it does not know what those objects are, it detects it as unknown. But then it gets the labels for these objects in the next task, and now is able to update the same tasks and say that there's an apple and there's an orange the next time without forgetting the person. Right? If you still see here, there is still an unknown object here because that was not given as a labeled information in the current task. So we still have to consider that there could still be other unknowns, but whatever the user is willing to label for us, we'd like to update the model in this kind of a setting. Okay, this allows us to learn continually based on what kind of supervision is available and what kind of data is available for a given setting without forgetting the past. Okay, so we also show, obviously, since it's published, we also show that the numbers work out reasonably well and we do better than previous approaches on this kind of a task. Okay, if you're interested further, this paper is also publicly available and the code is also publicly available. In fact, the code has about 750 stars and 117 forks on GitHub. And it's been fairly well followed by people in the community who are trying to extend this to various other settings. Okay, let's see how much time do we have. So we have about 2-3 minutes. Maybe let me skip the other efforts. I'll very quickly talk about them and come back to open questions and challenges. One of the other directions which we've also looked at is active learning. Active learning is about where you have a lot of data, but then annotating the data could be costly, right? You may need sometimes, let's say it's bioinformatics data. You may need somebody with significant amount of expertise to label the data. And they may not sit for you and sit for hours together and label 10,000 or 1 million data points. They may say, I'll give you 2 hours. You tell me what you want to label. I'll only label those. So then active learning is about picking the most useful examples which can be labeled by a human so that you can learn only from that pot of labeled data rather than the entire data set which you may have, for which labeling may be very, very hard. So in this context, we have tried learning, we have multiple efforts in this direction. One of our recent efforts looked at how do you know now do adaptive supervision, right? If you're trying to learn an active learning framework for object detection, when do you really need a person to give bounding boxes? And when can the person just name the objects in an image and you'll figure out the bounding boxes automatically? When is it enough for a person to point in an image, point at an object in an image? And when is it important for a person to exactly draw the tight bounding box around the image? All become important ways of getting supervision for a given setting. And we show that we can develop a method which can adaptively get supervision for data points based on each of their difficulty. Okay, we also do some work called adversarial data programming, where we automatically generate labeled data for a given task using a GAN-based framework. We've also worked on domain generalization and zero shot together, where you train a model on a set of domains. As I said, it could be autonomous navigation where you have trained a model on daytime, and now you want to work at nighttime. But then at nighttime, there is a new task or a new class that comes into the picture, which you've never seen so far. It's a new domain, but also a new class, zero shot domain generalization. Okay, how do you work in that setting? We also have a few methods in this direction in the last couple of years. We've also been more generally looking at zero shot learning, where we try to use the attributes of a class to learn the model without having access to the data itself. We've also looked at data generation for different weather. Ourselves explored autonomous navigation and agriculture. So where you have a model that probably gives you the steering angle at daytime, right? But now if the same environment becomes foggy, how does it work becomes an important question to ask. So we try to generate data that makes it difficult for a model to learn so that that data can then be further used to update the model and learn better over time, especially when you may not have enough labeled data from different weather conditions. That may be very hard to generate. You cannot have a Google car going through every street in every weather condition. It may just not be feasible, right? So you probably need these kinds of data generative approaches to compensate for this limited supervision and limited label data that you may have. Just a quick minute or so to look at open questions and challenges in this space before we stop. So as you can see, the paradigm of learning with limited supervision or limited label data is humongous in terms of its settings, because it depends on what kind of data, what kind of label, and at what time you have what access to what kind of data, right? All of that decides what method you can really use. Based on that, we have several paradigms over the last few years. You have zero shot learning, one shot learning, few shot learning. You have continual learning, you have transfer learning, domain adaptation, domain generalization, so on and so forth. But how do we now unify all of this becomes an important challenge as we go forward. As humans, we're pretty good at unifying these paradigms, right? So we don't need a different model for doing all of this. We are one person that does all of these things at the same time. How do you come up with models that can do all of this at the same time becomes an important problem, and also an important step in going from narrow AI to what is called as AGI, or artificial general intelligence. When can one transfer, right? So if you have two models, two domains, two different settings, should you always transfer models? Will it always work to transfer models? When can one manage to learn with limited label data? And when can one transfer from one domain to the other? How do you quantify all of this? Becomes a difficult question and also important question, right? So this is a very common problem in the industry, because I could imagine I'm a startup or any company that's building machine learning models. I've built it for one customer now. I've used up a team of mine for the last 6 months and built a machine learning model. Now a new customer comes and asks me exactly the same requirement, right? So now can I transfer from the previous customer's information and then do this quickly? Becomes an important question to answer. But a sub question that comes up in that direction is my previous customer may not be willing to share their data or models with another customer. There could be confidentiality issues. how do you then transfer in a privacy preserving manner becomes also an important question in these kinds of settings. And even more interesting problem here is that as data demand is being increased using supervised methods, how do you address the compute demand? Right? A few years ago, there was an interesting paper in natural language processing that showed that a transformer architecture with 213 million parameters, which is not too much. Today, you have transformer architectures with even billion parameters, uses up the carbon footprint of the lifetimes of 5 cars, okay, including fuel. Right? Just training one transformer using neural architecture search with 213 million parameters, just training one transformer model, okay, on a data center uses up energy equivalent to the lifetimes of 5 cars. And we are now talking about carbon footprint and reducing emission using cars and things like that. And on the other hand, we're building deep learning models that are deeper and deeper and deeper. Right? So now how do you learn from a limited label data becomes very important, so that you don't have very humongous models and humongous data and create a monster of a problem as much as we try to use AI to solve problems, right? So it's an important consideration to keep in mind as we go through in the next few years. I'll stop here and I'll be happy to take questions. Thank you again for the invite and your patient hearing.
Thank you, Dr. Ravi. So if anyone has the questions, please feel free to post them via chat box or you can unmute and speak.
Okay, I see a few questions. Let me probably just look at chat and answer them. There's one question that asks, can Merlin be utilized for medical imaging applications for the detection of diseases? Of course, yes, right, very much. So I don't think Merlin has any restrictions in terms of which domain it can be used in. It can be used in any of the domains. There's no restriction from a domain perspective, as long as the rest of the setting matches the domain's setting. There's a question from Devika, which asks, how exactly is domain adaptation different from domain generalization? Okay. Is it just about having a different target domain? Exactly. Right. So domain adaptation is where you have two domains, a source and a target domain. You have labeled data from both domains. You only want to improve performance on the target domain using data from the source domain. That's domain adaptation. In domain generalization, you don't have data from the target domain. You only have data from the source domains. You have to now learn a model which can directly work on a target domain. Right? As I gave you the example, I can now learn to drive a car. I mean, let's assume detect objects or detect roads and pedestrians and traffic lights and all of that in a sunny domain and in a rainy domain. Now, suddenly somebody could give me a snowy domain. I've never seen snowy domains in my data set before. But I still have to detect a pedestrian similar to how I detected a pedestrian in sunny weather or rainy weather. So I have to do that in a new domain, which is a snowy domain, right? So that's domain generalization. Right? In domain adaptation, you have access to the snowy domain data even during your training itself. You are only trying to improve performance on that. Domain generalization in that sense is a bit more challenging and harder to solve. Okay, let's see. What can be the possible instances of using supervision with graph data? I think all of these, to be honest, I don't think any of these methods are restricted to a particular kind of data. As I said, it only depends on at a given point in time. Based on that, you have to decide whether one shot, continual. People have actually extended these also over the last few years. But any of these can be extended. It depends on your problem setting with graph data. Right? Data, whether it images, text, or graph, is just data. I don't think any of the methods that I discussed here directly have a bearing on the data. Of course, the architectures have a bearing. That's why we had to use a certain architecture, but the core ideas themselves can be used with any other data set too. Right? It doesn't really matter from that perspective. You have to adapt it to a target architecture though. Okay, there's one other question, how to reduce the carbon footprint? How can we apply these techniques in the NLP domain? As I said, you can apply these techniques in the NLP domain, just repeating the same answer. It's exactly the same. I don't think, because it's very similar deep learning models that are used in different domains these days, you can apply many of these techniques in NLP too. You have to adapt it though, right? I talked about using faster RCNN for object detection. If you're using a transformer in NLP, you have to accordingly see which layer to introduce these ideas, right? So that's something you have to adapt. But otherwise, the idea can be used even for NLP or graph data or any other data set for that matter. How to reduce the carbon footprint? I'm not sure if it's directly in my regime, but we obviously want to use data centers less. We don't want to rely on models that have billion parameters. We don't want to have models always needing millions of training data points to learn from. All of them lead to carbon footprint, right? So if you can learn from only 1,000 data points using a model that has only 1,000 parameters, that would be ideal. But unfortunately, we don't get very strong models using this kind of an approach. So I was connecting this to the topic of deep learning with limited label data, because that's why deep learning with limited label data is important, because you want to come up with models that can learn with limited label data so that your learning can be more efficient, effective, and thus consume lesser energy in the process too. That's a completely different angle, but that's also important, is what I was trying to say in this particular scenario. Okay, one more question is, are the concepts of stability plasticity trade-off and exploitation exploration trade-off similar, perhaps on a high level? You could say so. Yes, you could say so. They're different in their own ways, but yes, that's an interesting connection, though. Say that they are in that sense. Exploitation, you could say, is like stability. Actually, you know what? Probably not. Probably not. I think the true trade in exploitation, you typically try to exploitation exploration trade-off used in active learning. If you have a certain amount of uncertain data, you try to learn from that group of uncertain data to train your model. Exploration is where you try to say, even if you have a set of uncertain data, let me go to some other region and check how uncertainty could look there in that region of data points, right? So I don't think you do this with continual learning, right? So that is required in active learning to cover the space, but you don't do that necessarily in stability plasticity trade-off. So I think I can see where you're coming from, but I think there is a difference too between these two. Okay, I think maybe just one last question. I know we have to stop from Devika, which is, okay, let me take one other question from somebody else. Nitesh has a question, which is deep learning with limited supervision going to replace unsupervised learning as a complete data-centric approach on learning without relying on labeled data? Not really, right? It's not about replacing unsupervised learning. It's about learning with what you have. That's what I'm trying to tell, right? So that's why I said that it's not that the cake is monolithic. There are several layers in the cake. Depending on what you have access to, you have to learn. As humans, we learn with what is provided. Right? You can ask questions and learn, but otherwise, with whatever, some data may be labeled, some data may be unlabeled. You have to learn with what is provided. It's not about replacing unsupervised learning. I think unsupervised learning has its own place. Sometimes you may just want to cluster. You may not even want to do anything further. That has its own place. But what we're talking about is, what if you were in between supervised learning and unsupervised learning? What if I don't have large amounts of labeled data and it's not unsupervised either?